By the end of this video, you should have a good understanding of bubble sort. So let's get into it. Bubble sort is very similar to selection sort in a lot of ways. Bubble sort, selection sort, and as you'll see in a future video, insertion sort follow some of the natural techniques people use for sorting things. These sorting methods will serve as a good introduction to sorting, but they are rather slow performance-wise. The core idea of bubble sort is to continuously loop through the data and swap values sequentially so that the lower values essentially float to the end of the array like a bubble. Let's start with an example using our good friend, the array of 5, 6, 1, and 12. We start with the first value and compare it to the value after it. If it's higher, we swap them. Since 5 is less than 6 though, we do nothing at first. Next we move to the right in our array, and we compare 6 and 1. We can see that 6 is greater than 1, so we swap them. To finish off our first iteration, we compare 6 and 12. And once again, we can see that 6 is less than 12, so we do nothing. This leaves us with the array of 5, 1, 6, and 12. Because the larger value always ends up on the right after every check, we know that the highest value in the array is all the way to the right and therefore in its final position. This means that for the next iteration, it can be ignored and we can deal with an array that's one smaller. We're only concerned with sorting the numbers 5, 1, and 6 in our case now. So we start with comparing 5 and 1. We can see that 5 is greater than 1, so we swap them. Next we look at 5 and 6, and we can see that 5 is less than 6, so no change is necessary. We're left with the array of 1, 5, 6, and 12. At this point, we can see that the array is sorted, but the algorithm doesn't know that, so we have to do one more iteration, which is just the comparison between the first two values, since we know that 6 and 12 are in sorted order. Since 1 is less than 5, the algorithm knows that the array is sorted, and it can now stop. One of the ways that bubble sort knows that it's done sorting is if it goes through an entire iteration and doesn't do any swaps. So it's possible to go through your first iteration and not swap anything, and that means that your array was already in sorted order and the algorithm can exit very quickly. Bubble sort can also end when the working area becomes smaller than 2 and there's no more swaps to be done. As stated before, bubble sort is a pretty slow sorting algorithm. You shouldn't be using it in actual programming projects, however it is slightly better than selection sort because an early stopping case can be added to the algorithm as I was just talking about. In the case of a sorted array, you get the best case runtime for bubble sort, which is O of n. This is about as fast as sorting algorithms can get. In comparison, selection sort's best case was still O of n squared, which is a huge difference. The average and worst cases for bubble sort are still the same as selection sort at O of n squared though, which isn't ideal. Performance-wise, the difference is just that bubble sort deals with partially or fully sorted arrays much better than selection sort does. But when dealing with fully random order, the algorithms are pretty much the same in terms of performance. Another somewhat important similarity between bubble sort and selection sort to note is that bubble sort is in place and therefore has a spatial complexity of O of 1. It doesn't need much extra memory to be performed. With the explanation out of the way, it's time to see how the code for this algorithm would work. Once again, I'll be using Python since pointers aren't necessary. In lower level code, the Python lists can be swapped for arrays since the main operation being performed is just value updates. So I'm starting with a bit of code here. This is just a random dataset generator. This is the same one I used in the previous video. If I print out random list 6, you'll see that I just get a random list of 6 values. This is just for generating datasets to sort. Anyways, let's create a bubble sort function. So if you remember the procedure, there's kind of 2 loops to consider here. So in a single iteration, you go through your array and you swap the values. But then you have to do those iterations multiple times, so you have 2 loops. The outer loop just needs to keep track of how much of the array we're dealing with at that point. So let's say for sorted count in range len target list. So we're keeping track of how many values we know to be sorted. Remember how after your first iteration, you know that the value all the way on the right is in the correct position, and therefore you can just forget about it. So you can keep track of the count you have sorted, so the amount of values you have on the right that you can ignore, so that you don't handle them when you do your normal iterations through. So we have this loop, which is our outer loop, and then we have to do our inner loop, which is the looping over the individual values and swapping them. So we do for I in range len target list. Excuse that I that popped up there, I don't need that. And then this is just looping through all the values in our list, but we want to ignore the sorted values, so we can subtract that from our loop. So we get the amount of values that are remaining to be sorted. And then from this, because you're swapping, you're going to want to subtract 1, because, for example, if you have an array of 2, you start at index 0 and you swap 0 with 1 potentially, but then you're done. You don't do 2 swaps because you have 2 values. You always do 1 less swap than you have values, so that's where that -1 comes from. So we have our 2 loops, and this is the general structure for looping over our array here. Now we can do our swapping. So if target list I is greater than target list, and then you look at the next value after it, so I plus 1, then you swap it. So I'll do the Python swapping thing here. You can create another variable to do the swap, but in Python you can do it without creating the extra variable by just doing this. And then this should theoretically sort our list, so we can do return target list. So I did not add the early stopping case that you can add yet, and that's because I want to show you the difference it makes when you add that. But first, let's just demonstrate that this works. So let's do print bubble sort, and let's take our my list. So if you look down here, you can see that we have -4, 0, 1, 3, 5, 17, 92, and 231, which is sorted order, so our sort is working. If we want, we can actually just print out what our list looks like after each iteration, so you can just get an idea of what it looks like. So target list. So I can remove this because it'll print out its ending state regardless. Or rather, not quite. I do have to still run it, but you can see what happens here after each iteration. I won't go too in depth here because you can just like pause the video and look through this. I'll pull this out and you can look at it and see how this is working. And if you're writing the code yourself, you can experiment on your own to get a better understanding of how this works. So let's check and see how it does with a larger array. So let's do bubble sort random list 5000. So we can see it took 3 seconds. If we do 10,000, we can get a good idea of the runtime. So we got about 11 seconds. We went from like 3-ish seconds to 11 seconds. And if I doubled the amount of values, and it took significantly more than twice as long, and twice as long would have been, what, just under 6 seconds. Since it's significantly more than twice as long, and we can see that we have 2 loops here, it's pretty safe to assume that this is O of n squared. And I did talk about that earlier. Anyways, so let's do something interesting and make sure that our sorting is accurate by taking this and comparing it to the Python sort of the same thing. So we can just do this and print it out, and this is a good way to check to make sure your sort is working properly. Oh wait, actually that's not correct. We need to generate this first, so they're using the same thing. So random list equals that, and then we take the copy, and then we put the same thing in here, and then they're dealing with the same array. Oops, that should be sorted. And we get a true, which means that the data is the same, and therefore our sorted order is correct. So it's time to look at something interesting here. And this is the early stopping thing I was talking about. So we can do sorted data equals sorted RL. And let's pass the bubble sort our sorted data. Oops. So if we run that, we can see it takes about 1.5 seconds. We can run it again, 1.5 seconds. But we can make this go much faster if we add our early stopping case. So all we have to do is go right here, and for each iteration we just take like a variable and say swapped equals false. This keeps track of whether or not we swap something in this iteration, and if we do swap something we say swapped equals true. But if we get to the end of an iteration and swapped is still false for some reason, that means that all the values must have been in sorted order. So if swapped is false, or the other equivalent for this is just if not swapped, then we break out of our loop and we're done sorting. So with that early stopping, we can run it, and you see that drastic drop. We went from like 1.5 seconds to under 0.1 seconds. That's huge. And just to show that the sorting still works, I'll throw in the my list and print that out. And you can see it's in sorted order. Alright, that is it for this video. I'll leave the source code in the description if you want to take a look at that. Hopefully I'll see you in the next one.